Hi there, and welcome back to Leon Reads, the channel where we share powerful insights and personal growth lessons through great books. Imagine traveling through space at nearly the speed of light, peeking inside black holes, and calculating how many aliens might exist all in one book. Sounds crazy, right? Well, that's exactly what Welcome to the Universe offers. It's like a cosmic road trip, guided by three world-class astrophysicists with a great sense of humor. While you enjoy what you hear and want to dive deeper, we've included a link to the book in the description below. Now, let's get started. Welcome to the Universe 2016 is a fascinating book written by three of the most brilliant astrophysicists of our time, but unlike many academic heavy science texts, this book adopts a witty, accessible tone to introduce readers to some of the universe's most fundamental concepts such as black holes, galaxies, and time travel. Beyond that, Welcome to the Universe also poses a profound question. What is humanity's true place in the cosmos, and are we alone? Neil deGrasse Tyson is an astrophysicist, director of the Hayden Planetarium, and host of the popular Star Talk podcast. In 2015, he was awarded the U.S. National Academy of Sciences Public Welfare Medal for his contributions to science communication. Michael A. Strauss is a professor of astrophysics at Princeton University. He is well known for his work on quasars and his contributions to mapping the distribution of galaxies. Richard Gott is also a professor of astrophysics at Princeton. He has proposed influential theories on time travel and made significant contributions to cosmology, general relativity, and even the controversial doomsday argument. The universe is 13.8 billion years old. To grasp that timescale, imagine the entire history of the universe compressed into the length of a football field, where each step represents 50 million years. Where, then, would the entirety of human history fall? The answer, right at the very end, thinner than the width of a human hair. Although humanity occupies only a sliver of cosmic history, we often like to think of ourselves as central or important. This book corrects that perspective, inviting readers to hop aboard a whirlwind journey through the cosmos with the authors as your guides. Before venturing further into the universe, the authors remind us to locate our starting point, Earth. For many, this feels like the beginning of their cosmic journey, but in fact, you've been traveling through the universe your entire life. Our planet is already a spacecraft, moving through the solar system at nearly 100,000 kilometers per hour. From space, take a look at Earth. Tilt your head just a little to the right. Why? Because only then will you be seeing our planet straight on. As we learned in school, Earth's axis is tilted at 23.5 degrees as it orbits the Sun. Now look toward the edge of Earth. Do you see that shadow? As we know, Earth is always split into two halves, day and night. While the planet rotates, one side faces the Sun while the other is hidden in darkness. That rotation is what gives us day and night. Of course, there are exceptions. In December, during the summer solstice at the South Pole, sunlight can shine for 24 straight hours. But for most of the planet, the balance is always 50-50. This tilt is also what determines everything we know about the sky, from the Sun's path to the constellations overhead. Many assume that when the Sun is high at noon, it must be directly overhead. But in the United States, you will never actually see the Sun at the zenith. It is always at an angle. This also explains why you'll never see the same constellations as people living in the southern hemisphere, and vice versa. From Earth, the Sun may appear yellow. In reality, however, the Sun is a bright white star, not yellow at all. It burns at a temperature of about 6,000 Kelvin, roughly 5,726 degrees Celsius, slightly hotter than an ordinary flame. A star cooler than the Sun, for example, at about 1,000 Kelvin Setecentesi Vinci says graus Celsius, would appear red, because at lower temperatures, light shifts toward the red part of the spectrum. But whether hot or cool, every star contains a nuclear fusion furnace at its core. The hotter the star, the faster it burns through its hydrogen supply. That is why the hottest, bluest stars live the shortest lives, about 10 million years, while cooler stars, like our Sun, can last around 10 billion years. If we could cut open the Sun and look inside, we would find a glowing core, the nuclear reactor at the heart of the star. Not only does this furnace keep the center blazing hot, it also creates the chemical elements. In such extreme heat, the normal rules of electromagnetism break down. Protons, which normally repel each other, are forced close enough to fuse. This process forms new kinds of matter. At the Sun's core, roughly 4 million tons of matter are converted into energy every second. Nearly all of this comes from hydrogen atoms fusing into helium. This fusion process sustains the Sun for about 90% of its lifetime, producing the heat and light that make life on Earth possible. Eventually, about 5 billion years from now, the Sun's hydrogen will run low, leaving only helium. At that point, the core will grow unstable, heating up and collapsing inward. The outer layers will expand into what we call a red giant. As the red giant grows, its core becomes hot enough for helium to fuse into carbon, and later, carbon into oxygen. The result will be a layered core, like the layers of an onion, each representing a newly forged element. Finally, the star will burn out, collapse, and eject its outer layers back into the galaxy. That will be the sun's fate. Larger stars, however, can end far more dramatically in a supernova, leaving behind a neutron star or even a black hole. But long before any of this happens, Earth will already be scorched. In just about 1 billion years, the sun will grow hot enough to boil Earth's oceans, evaporating them into the atmosphere. At that point, life as we know it will cease to exist. When stars explode, the debris they release can coalesce into rocky planets rich in oxygen, silicon, and iron. In other words, stardust becomes worlds. In our own solar system, we have 8 planets. Looking out the window of our imaginary spaceship, we first pass the inner rocky family: Mercury, Venus, Earth, and Mars. Each is unique, but they all orbit close to the sun and are composed primarily of solid matter. Shifting our gaze outward, we encounter the gas giant family: Jupiter, Saturn, Uranus, and Neptune. Again, very different worlds, but they share a common trait: immense size and low density compared to the rocky planets. And then there's the oddball, Pluto, once considered the 9th planet. Pluto's planetary status has been heavily debated. No offense to Pluto, but it doesn't really fit with either family. Its orbit is unstable and unusually elongated. Scientists argue that's not how a planet should behave, and since 1992, astronomers have discovered over 1,000 Pluto-like bodies, icy worlds beyond Neptune. Together, they form the Kuiper Belt. Pluto is simply the largest and brightest among its true siblings. By now, you might be reaching for a blanket, because space is incredibly cold. The universe carries only the faint afterglow of the Big Bang, and it is expanding rapidly. Today, the cosmic temperature is just 2.7 Kelvin, about minus 270 degrees Celsius, and still dropping. As we venture beyond the solar system, you'll notice that the night sky is filled with dazzling stars. But there are a few common misconceptions about them. For instance, you may have heard that the North Star Polaris is the brightest star in the sky. That's not true at all. In fact, Polaris doesn't even rank in the top 10, or the top 20, or even the top 30. It's only the 45th brightest. The real brightest star in the night sky is Sirius, also known as the Dog Star. Another frequent misunderstanding involves time and distance. Take the sun, for example. Although it feels close to us, it is actually about 150 million kilometers away. In astronomy, we don't measure distance in kilometers or miles, but in units of light travel time. Since light travels at 300,000 kilometers per second, the distance between the Earth and the Sun is about 8 light minutes. In other words, it takes sunlight 8 minutes to reach us. Our closest stellar neighbors, the stars of the Alpha Centauri system, are about 4 light-years away. This means the light we see from them tonight was actually emitted 4 years ago. In a very real sense, whenever we look out into space, we are looking back in time. But what exactly is light? Light is made up of photons, which behave as both particles and waves. Because photons carry different amounts of energy, they come in different flavors. One of these is visible light, the part of the spectrum our eyes can detect, which includes white, red, orange, yellow, green, blue, and violet. Beyond that, there are flavors invisible to us, such as infrared, microwaves, and radio waves, all of which lie on the red end of the spectrum. On the opposite, higher energy end are ultraviolet X-rays, and gamma rays, the violet side of the spectrum. As you move along the spectrum toward gamma rays, the energy of each photon increases. That's why doctors warn us to wear sunscreen to protect against ultraviolet rays, and why X-ray rooms are shielded with lead. As we drift through the Milky Way galaxy, you'll see that stars are not solitary wanderers. Instead, they form clusters. Some contain just a few hundred stars, known as open clusters. Others pack in hundreds of thousands of stars. These are globular clusters. In either case, all stars within a cluster share the same birthday, having been born from a single giant cloud of gas and dust. Ahead of us lies the Pleiades, an open cluster less than 100 million years old, brimming with hot, bright, young blue stars. As you might remember, such stars burn extremely hot. Yet nearby, you'll also spot cooler, redder stars. Soon after, we pass through the Orion Nebula, a vast cloud of gas and dust within our galaxy. This is a true stellar nursery, where about 700 new stars are being born at this very moment. These nebulae are enriched with heavy elements, created in the dying core of older stars. Gravity then pulls the gas and dust together, giving birth to new stars and, in some cases, new planets. The Milky Way itself contains anywhere from 100 to 300 billion stars. They form a flattened disk spanning about 100,000 light-years across. Toward the center, the stars become denser, packed into a bright central bulge stretching some 20,000 light-years. But here's where things get even stranger. The visible matter in the Milky Way, the stars, planets, and gas clouds, doesn't add up to the galaxy's total mass. Something else must be contributing. Astronomers have hypothesized the existence of dark matter, an invisible substance that accounts for most of the galaxy's mass. Though we can't see it or identify its fundamental particles, its gravitational pull is undeniable. Dark matter is mysterious enough, but there's something even more mind-bending at the center of our galaxy. Observations show that stars there orbit around an invisible object with a mass about 4 million times that of our Sun. Can you guess what it is? In the next chapter, we'll talk about it and about its cosmic siblings. In the cosmos, there exist objects so massive that not even light can escape their pull. These are black holes, often found at the centers of galaxies. As mentioned in the previous chapter, the core of every galaxy contains a dense bulge, usually hosting a supermassive black hole, compared to others. However, the Milky Way's central black hole is relatively modest, only about 4 million times the mass of our Sun. By contrast, some black holes in other galaxies can weigh several billion solar masses. But what exactly makes them so mysterious? Let's think about escape velocity. If you toss a ball into the air, it rises and falls back down. But if you throw it fast enough, at about 25,000 miles per hour, it will escape Earth's gravity completely. Now imagine an object so dense and heavy that the escape velocity is greater than the speed of light. That's a black hole. Even photons, the fastest travelers in the universe, cannot break free. So what happens if you try to rest inside a black hole? As long as you remain outside, you're safe. But once you cross the Schwarzschild radius, also called the event horizon, there's no turning back. This is the boundary where the escape velocity exceeds the speed of light. The Schwarzschild radius RS is the critical size at which an object collapses into a black hole. For the Sun, RS is about 3 kilometers. For Earth, only 9 millimeters. In other words, if all of Earth's mass were compressed into a marble with a 9 millimeters radius, it would become a black hole. This concept stems from Carl Schwarzschild's 1916 solution to Einstein's equations of general relativity. The problem is, the Schwarzschild radius is invisible. You would never know when you've crossed it. Once inside, tidal forces would begin to tear you apart. Step in feet first, and your legs would be pulled downward while your torso is stretched toward the center. Eventually, you'd be elongated and crushed into a thin strand like spaghetti. The official term is indeed spaghettification. Fortunately or unfortunately, depending on your point of view, spaghettification happens quickly. About 0.09 seconds inside a black hole with 3 billion solar masses. Still, no one outside could ever witness the process. Just as you cannot see what lies beyond Earth's horizon while standing on the surface. In a way, the universe is like a loaf of raisin bread. The galaxies are the raisins, and the dough is the space between them. As the dough rises, the raisins drift farther apart. From the perspective of any single raisin, all the others appear to be moving away. Similarly, from our vantage point in the Milky Way, all galaxies seem to recede even, though we too are in motion. Moreover, the farther the galaxy, the faster it recedes, since more dough is expanding in between. Of course, the analogy isn't perfect. A loaf of bread isn't infinite, but the universe may well be. And like the raisins, galaxies themselves don't expand, only the space between them does. So if the universe isn't literally a loaf of bread, what shape does it have? The answer depends on how many dimensions we consider. The universe has 4 dimensions, 3 of space and 1 of time. In 1922, physicist Alexander Friedmann illustrated this in a model shaped like an oval or egg. In Friedmann's diagram, time begins at the bottom with the Big Bang and ends at the top. At first, all galaxies rush outward, expanding until they reach a maximum size at the widest part of the oval. We haven't reached that point yet, as the universe is still expanding. After the peak, galaxies reverse course, drawing closer until they collapse together in a big crunch. Of course, this is only one possible model. The universe need not resemble an oval at all. It could just as well look like a Victorian corset. But whatever its ultimate shape, the time has come to explore one of humanity's favorite cosmic topics, time travel. In most works of science fiction, time travel is portrayed as stepping through some great portal, perhaps via a machine that sends you back into the past. According to Einstein, however, a true time traveler would need to move faster than the speed of light. And as we know, traveling faster than light is physically impossible. But what if you could take a shortcut? That's where wormholes, also called Einstein-Rosen bridges, and cosmic strings come into play. A wormhole is a tunnel connecting to distant points in curved space-time. In theory, some wormholes might even link to entirely different universes, like 2 funnels joined at their narrow ends. You couldn't pass through certain types of wormholes since they would require moving at light speed. But other theoretical wormholes might be traversable. So far, scientists haven't discovered any such wormholes, but mathematically they're possible. Here's how it might work. Imagine one mouth of a wormhole near Earth, and the other mouth 4 light years away, near the Alpha Centauri system. Yet the tunnel itself is only 3 meters long. Think of it like drilling a hole straight through a dining table. Ants trying to crawl from the top to the underside could walk the long way around the edge, or they could slip directly through the hole. You're not breaking any physical laws, you're just taking a shortcut. Now let's push this further into the realm of time travel. Suppose one mouth of the wormhole is anchored near Earth, and the other near Alpha Centauri. On January 1st, 3000, the massive spaceship tows one end of the wormhole on a round-trip journey at 99.5% the speed of light. From Earth's perspective, more than 5 years would pass before the ship returned. But inside the wormhole, time would tick 10 times more slowly. Only 6 months would have elapsed. So when the spaceship returns to Earth on January 10th, 3005, the mouth it carried is now time-shifted. If you jumped into the wormhole right then, you'd emerge near Alpha Centauri on July 1st, 3004.5 years earlier. And since Alpha Centauri is only 4 light-years from Earth in normal space, you could board another spacecraft, travel back at 99.5% the speed of light, and return to Earth by July 8, 3004, 6 months before you first entered the wormhole, just in time to shake hands with your past self. What about time travel via cosmic strings? These are unimaginably thin filaments, narrower than an atomic nucleus, but with colossal density about 1,000,000 trillion tons per centimeter, thought to be remnants of the early universe. They could stretch infinitely or loop back on themselves, like strands of spaghetti or even spaghettios. Cosmic strings are so heavy that their gravitational warping of space-time might, in theory, allow time travel lift to strings passed close enough together, but unless they align just right, it would take too long to circle them and actually reach your own past. Realistically, the odds of encountering to nearby cosmic strings are vanishingly small. Ultimately, unraveling these mind-bending possibilities requires a deeper understanding of quantum mechanics. To know whether time machines could exist, we must find a way to merge general relativity with quantum theory. Perhaps a future law of physics will prove time travel impossible, but for now, the door remains open and the hope alive. By now, you've learned quite a bit about the matter that makes up the cosmos, but perhaps the most intriguing question remains. Are there other intelligent beings in the universe besides us? Life as we know it requires many specific conditions. The first is the presence of liquid water. If a planet orbits too close to its star, water evaporates. Too far, and it freezes solid. In reality, things are more complex. Stars come in many sizes, so the habitable zone, the distance where liquid water can exist, depends heavily on the size and energy of the star. Based on what we know, a life-supporting planet must orbit a star similar to our Sun. But time is also critical. Evolution takes billions of years. That means both the star and the planet must remain stable long enough for life to emerge. The most massive stars, however, burn out in only about 10 million years, far too short for complex life to develop. That's already a long list of requirements. But it doesn't stop there. To ever interact with aliens, both we and they would need to develop advanced technology capable of sending signals across interstellar distances. Imagine a civilization 1,000 light-years away. Their message would take 1,000 years to reach you, stally meaningless for creatures who live only about a century. Still, some planets show promise. One candidate is Kepler 62e, a world with a radius 1.6 times that of Earth. It receives about 20% less radiation per square meter from its star than Earth does from the Sun. This suggests potential habitability, though it might just be a rocky or icy ocean world. We can't yet be sure. To tackle such questions systematically, astrophysicist Frank Drake devised the famous Drake equation, which estimates the number of potentially habitable planets in our galaxy. For example, within a spherical volume of space 40 light-years across, there are about 1,000 stars. Using the Drake equation, we might expect roughly 6 potentially habitable planets within that small neighborhood. And remember, 40 light-years is tiny compared to the entire Milky Way, let alone the universe. The harder part of the equation concerns the fraction of planets that evolve civilizations with advanced technology capable of interstellar communication. Here, the probability depends on the ratio of a civilization's average lifespan to the age of the galaxy. Unfortunately, we only have one data point. Some estimates suggest that the average lifespan of a technological civilization might be about 12,000 years, though this is far from certain. Using our best guesses, the Drake equation suggests there could be hundreds of civilizations scattered across the Milky Way, and yet, as of now, we haven't found any, and apparently, none have found us. Still, that only makes the search more exciting. The universe is vast, cold, mysterious, and endlessly captivating. Since humanity first began to grasp its immensity, we've had to abandon the belief that we are the center of everything. In truth, we are tiny compared to the cosmos, and it is entirely possible that there are civilizations out there far more advanced than ours. Reading Welcome to the Universe feels like being guided on a cosmic tour by 3 of the world's most brilliant astrophysicists. Yet, instead of burying us in technical jargon, the authors invite us along with humor, clarity, and a sense of wonder. What struck me most is how the book constantly redefines our place in the cosmos. On one hand, it humbles us, reminding us that human history is but a hair's breadth on the cosmic timeline, and that Earth itself is just a small speck orbiting an ordinary star. On the other hand, it empowers us, showing that through science, We've come remarkably far in understanding black holes, galaxies, wormholes, and even the tantalizing possibility of life beyond our solar system. The chapters on time travel and wormholes stood out as a perfect balance of imagination and physics. They remind us that while science fiction pushes boundaries, real science is not far behind in offering mind-bending scenarios that may one day shape our future exploration. Equally fascinating is the discussion of the Drake equation, which reframes the age-old question, are we alone, into something measurable, even if uncertain. Ultimately, Welcome to the Universe is not just a book about stars and galaxies, it's a reflection on curiosity itself. It shows us that asking questions, even the impossible ones, is at the heart of what it means to be human. And whether or not we ever find alien civilizations or conquer interstellar travel, the pursuit of these questions will always expand the limits of our imagination. The more we learn about the universe, the smaller we seem, and yet, the more extraordinary our curiosity becomes. Welcome to the Universe isn't just about stars and galaxies. It's about our place in the grand cosmic story. If you want to keep exploring big ideas like this, you can also buy the book to experience it more clearly, as well as support the author. I will leave the link in the description below for you to easily search. Don't forget to like, share, and subscribe. The universe is waiting.